So something about the dimensions is not right there. I'll show you a couple of options. So suppose you want to create a matrix, and you're going to go through a loop and go row by row, inserting something that you create into that matrix. So I will make, first way I will do it, let's say we want a sample of size 20, and we want to do it 100 times. I'm going to make an empty matrix, just putting NAs in there. I could put whatever I want. I'm going to fill them in. I want n rows, and capital N rows and little n columns. For I n1 to capital N, I'm going to put in the ith row, let's just generate some random normal data, a sample of size little n. So having it already created with whatever in there, could be zeros, could be whatever, a loop, and then the ith row. Another way to do it, if you didn't know how many rows you needed, you could do something like set up X to be kind of an empty placeholder, and then for I n1 to n, you could do X gets R bind, row bind, whatever X currently is with something new. So let's remove X. So X is nothing right now. But you can concatenate onto nothing, like concatenate X with that, just creates that. So now if I do this, I have 100 by 20. Does that make sense? Yep. So if you have a two-dimensional array, basic matrix, there's rows and there's columns, and if you want a subset, you have to say something about what rows you want and what columns you want. If you leave one of those blank, that means give me all of them. All right. So there is a new version of seqanalysis.r that was posted. The stuff that we're going to learn about how to align multiple sequences simultaneously uses the muscle algorithm and a corresponding muscle package, and I think it had been updated in recent months. So the syntax that was in seqanalysis.r did not work. It works now. The relevant part, by the way, is you can just search for muscle in this text file. It's down below what we're talking about right now. We're talking about if we just have two sequences, let's align them. And then we talk about if we have more than two sequences, multiple sequence alignment. So this part is new. Line 421. Okay, so let's go back and continue thinking about how to align two sequences, how to do pairwise alignment. This is that alignment.pdf file that I posted under Notes. And let's think about these two sequences. How should I optimally line those up together? We said we're going to employ an algorithm to find the best way. And in order to employ the algorithm, we have to decide on some parameters. And these are the ones we're going to use to illustrate it. So if, when I line things up, if at a particular location there's an A in the first sequence and there's an A in the second sequence, those lined up and they matched, I'm going to reward with a +1. If it was an A and a T at that same location, mismatch, it'll be a penalty of -1. And any gaps, like if I have to create a gap of length 1, I will impose a penalty of -3. If I have to impose create a gap of length 2, I'll do a penalty of -6, and so on. So it may be that the best way to put two sequences together is to put the first part of the first sequence here, and then a gap, and the second part of the first sequence over after that. It's okay to put gaps. It's just if you didn't have to have them, you wouldn't want them. So that's why we penalize for having gaps. Step 1 is to create a table like this where you put the sequence for the shorter sequence on the top and the sequence for the longer sequence on the side. And we start by putting in these numbers along the rows in the first column of, along the columns in the first row of numbers. We put penalties that happen every time we create an extra gap space. So if I create a gap in the first space, I'm not going to put that G with that G. I'm creating a gap in the first sequence. I get a penalty of -3. If I create another gap by moving horizontally, creating another gap in this sequence at the top, there's another penalty of -3, and again and again and again. And similarly, as you go down the rows, your vertical movements correspond to gaps in the sequence over on the side. And then the interior of the table, you put, if there is a match corresponding to the two sequences, you put your match reward. And if there is a mismatch, like this A with this G, you put your mismatch penalty. So we have a 1 there, we have a 1 there, and several other places, but everywhere else it's a -1 for a mismatch. Okay, after that, we're going to fill in with the actual score accumulation numbers. The ones that we just put in on the previous slide are the penalties kind of cell by cell. But now we're going to start stringing them together. If you were to do a particular alignment, add up the score, basically. So let's start in the first interior cell. And what we do is we consider possible ways of getting to that cell. The possible directions that we can get into this cell from are from the left, from the upper left diagonal, and from the top. So I can consider, suppose I start from here. This would correspond to starting this sequence here with a gap. So suppose I did gap and then G. To do that, I had to create a single gap. So to go from, actually this would correspond to a gap of length, let's see, what would it correspond to? So if I do this, I'm actually creating a gap in this sequence. If I do that, I'm creating a gap in this sequence. So this cell here corresponds to an initial gap in this sequence, the sequence on the side. Yes?
I don't understand why you put a gap in the longer sequence. Like on the first column, why is there a gap? There wouldn't be a need for that.
There wouldn't be. I mean, these could be the same length. They don't have to be one shorter than the other. In this case, definitely it does not work best to create gaps in the longer sequence, and most of the time it probably won't. just an example. You know, the algorithm that you're going to use when you say do pairwise alignment in R is going to do this. You know, it is possible, for example, if these were the same length, it would be more sensible, more realistic probably to have a gap in this one. But in principle, it's fair game to create gaps in either sequence. So basically what I want to do to fill in this cell is figure out how can I move from these three cells, left, upper left diagonal, and right, and straight up, how can I move to this cell and have the highest possible score? If I move from this cell to that cell, that's a horizontal move, and a horizontal move incurs a penalty of a gap, because a horizontal move is creating a gap. So if I were to go from this cell to this cell, I would have to take this -3 that corresponds to an opening gap in this guy, and then create another gap by putting one gap in this guy. So what would be the score at that point? Having done that, it would be -3 for this penalty, and then another -3 for creating this gap. So if I wanted to start here and go here, my score in this cell would be -6. That's one possibility. Another possibility would be to move, let's look at this one, to move down. And if I move down, the same issue applies. I'm creating a gap. Every time I create a gap, that's a penalty of -3. So if I were to move from this cell down to that cell, I would have -3 and another -3. I would again have -6. And then think about diagonal. If I were to start here and move diagonally, that would correspond to no gaps no gaps yet, and putting this G with that G. When you move diagonally, there is no gap penalty because you didn't create a gap. The only penalty / score has to do with, was this a match or a mismatch? So I take this 0, the existing score for the cell I'm about to move from, and I do not do any gap penalties. What I do check is it a match or a mismatch? And in this case, it was a match, so my penalty, or my score, is 0 + 1. And that was the best possible move. The other two possible moves gave me a score of -6. So the number I'm going to put in this cell is the best possible score, and I'm going to add an arrow to the upper left diagonal to indicate that's where it came from. Let me show you some more examples. You do it a few times and you get kind of the hang of it. Let's go to the next cell over, this guy. The same possibilities apply. I can move into this cell from the left, from the upper left diagonal, or from the top. If I move from the left, I start with a score of 1, and to move to the, if I move horizontally, I incur a penalty of -3. So my score, if I were to make that move, would be 1 - 3 or -2. If I were to move from the top, I'd have this -6 corresponding to 2 gaps in this guy, and now I'm going to align. Now I'm going to create another gap, so this would be -6, -3, or -9. If I go diagonally, I start with -3, and I have to subtract another one because this A does not match the G. So if I moved diagonally, I would have a score of -4. So in this one, the best move I can make is to create a horizontal a gap in the first sequence, corresponding to 1 - 3 or -2. This one is the same exact story. I could do -2 - 3 to get -5, or I could do -6 - 1 to get -7. That's worse. Or I could do -9 - 3 to get -12, which is also worse. The best move is to go from here to there, another gap. And finally, this one, if I go from -5 and create a gap, that's another -3 penalty, so -8. And if I go diagonally, I would take this -9 and no gap penalty. All I need to do is check, does this G match that G? It does. So I would do -9 plus 1 to get -8. So there are two moves that I could make that have the same score. That's why I have an arrow going left and an arrow going upper left diagonal. And then you fill this out for the rest of the cells and add those arrows to indicate which cell or cells you moved from. That's the completed version. They color-coded the arrows. For your homework when you do this, just FYI, well, you might find it most convenient to make this table first, depending on how you're going to make this, and like put it in your assignment. It can get crowded to put all that stuff in there. You could make this table and say this is my template table, and then this table without those numbers in the upper left, just to keep it cleaner. You could make this table again with only these internal numbers and your arrows. If you want to do it by hand, that's fine. And you can if you want to. I did it in LaTeX. You could do it in Microsoft Word. Yeah, so let's see. Let's go to, the question was, can we go through an example on a whiteboard? So let's go to this that we did here. This is the same as is in the slides. So let's just do this. This way you can compare back to the slides. I think that's the same. No, it's not the same. So I have a different set of sequences. Let's do this. I'm going to come over here, and I'm going to make a table. Let's write these sequences. So GAATTC is the longer one. GAATTC. And the shorter one is GATTA. I'm going to put, let's do, what are we doing back here? We're going to do the function we're going to use to do this in R is called pairwise alignment. This comes from this package. I don't know if we saw this package yet. Different package. And to use this function for aligning two sequences, we are going to have to provide both sequences, the first one, the second one. We are going to have to provide what's called a scoring matrix or a substitution matrix. And there is a function that we can use to create one of these. All you have to do here is specify what's the match reward and what's the mismatch penalty. Let me run this as we go. So let's get biostrings installed. So once this is installed, I'll show you what this looks like. It's a simple thing, and again, you can just use this function to do it. The other thing that we're going to specify is what happens with gaps. So this score matrix or substitution matrix is basically what happens when you get an A with an A, what happens when you get an A with a T, and so on. So this is going to be a 4x4 matrix. So we could go ahead and keep working on our table over here. We are going to do gap opening -2, gap extend -8. Those are going to be arguments that go here in the pairwise alignment function. So I'm going to have to provide a substitution matrix and what happens with gaps. And the way that the pairwise alignment function works is gap opening is a penalty that's going to happen every time you have to create a gap. Gap extension is going to be a penalty that applies to every single space in your gap, including the initial one, which is a little bit weird to me. What that means is that if you were to create a gap of length 1, you would have a penalty of gap open and gap extend. So if you want to match what the slides are doing, the way they present it, they just say we have one gap penalty. And if you create a gap of length 1, it's that penalty. If you create a gap of length 2, it's 2 times that penalty, and so on. The pairwise alignment function operates a little bit differently. And for illustration purposes, we're going to say gap open penalty of -2, and every extra space, or every single space in the gap, gets a penalty of -8. How about, in order to match what is in the slides, why don't we make this 0, and let's make this -3. So that's like what's in the slides. For your homework, I think I said which parameters to use, like mismatch penalty, match reward, and all that. But yeah, you want to do what the slides are doing, so I think in the homework you do want gap open equal to 0. So we will do that, and let's go ahead and do this to also match what's in the slides. So I'm going to do match reward 1, okay. Now over here, I can start filling this table in, and I'm going to want it to look like this. So I will start with a 0. And then going down the rows in this first column, I'll start accumulating gap penalties. Along the top, I'll put our second sequence, which is GATTA. So I am going to leave this blank and start here. So we'll do it up here. GATTA. Okay, and then accumulate gap penalties across this second sequence. Okay, and then the next step is to fill in the matches and mismatches. So I'm going to go cell by cell. The G in the first cell, first row, first column of the interior matches. So I'm going to give myself a 1, mismatch, 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 mismatch. Okay, and then I'm going to go cell by cell and start asking that question. What's the best move I can make to get into this cell? Applying these penalties that we just put in. So if we start in the first row, first column of the interior, what could we do? We could go from here to the right. If I went from there to the right, what number would I put here? It'd be -6. If I went from here to the bottom, same thing, right? But if I go diagonally and actually put the two G's together, I take this 0. I get no gap penalties because diagonal moves, I'm not doing a gap. And the only thing I need to do to that 0 is add a 1 because the G matches the G. So this right here is going to be a 1. The next cell over, I'll just try to do these kind of quickly. I could do 1. I could take that 1 and move horizontally, or I could take that -6 and move vertically. Or I could take this -3 and move diagonally. So if I move horizontally, I take my 1 and I subtract 3 for a gap. So I would get -2. If I were to move diagonally, I would take that -3 and I would subtract another 1 for a mismatch. So I'd get -4. And if I move vertically, I would get -9. So I'm going to move horizontally. Let me add, before we move forward, let me add an arrow to indicate that's the move we made. Now we're going to move horizontally and give ourselves a score of -2. Does that make sense? Okay. So it would take a little while to fill the whole thing out, but that's the way you do it. You just keep going. So let me go back to the slides and go to the end. We wind up with something that looks like this. It's messy, but it contains the information that you need to actually do the alignment. So the key is, in order to have a valid alignment, we have to traverse this whole array and end up in the bottom right cell. Bottom right cell is kind of like the completion of the alignment. Any trajectories that take me to another cell, like it's possible to get to this cell. If I follow a certain set of arrows, I would get all the way down to here. That's not a candidate for best alignment. Best alignment candidates are here, correspond to arrow trajectories that end here, like the blue arrows. The blue arrows follow through here and end up in the bottom right. The green arrows do, the purple arrows, so that's why they have colored arrows in there. Those are all optimal alignments that wind up with the same final optimal score. So let's understand what these are saying. Let's follow the blue arrows, for example. The blue trajectory says, initially, put this first G with that first G. We didn't do any gaps. We just stuck them together right at the beginning. Then we did the same thing. We put the A with this T. We got a mismatch, but that was still the best move we could have made overall. And again, we put the next letters together, and the next letters together, and the next letters together, and then we have 1, 2 gaps in this, let's see, moving vertically. So this is going to be G, A, G, A, blank, blank. So actually, vertical moves create gaps in the top sequence, and horizontal moves create gaps in the side sequence. This blue trajectory says, line up the two sequences like this. We're going to do G, A, G, A, gap, gap. G, A, G, A, gap, gap. Lined up with G, T, 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 A, G. And this has a score of -7, which is the best you can do. According to this algorithm and according to the parameters that you chose, that is an optimal alignment. There are others. Let's follow the green one. The green trajectory says put the first G with the first G, because we went diagonally. The green arrow is basically hidden behind the blue arrow in this case, but we still went to this cell, which corresponds to putting the G with the G. But then we create gap, gap. Vertical moves, gaps in the top sequence. So we're going to do G, gap, gap. After doing that, we are going to put this A with that T. And then we're going to put the next letters together, the next letters together, the next letters together. So basically this alignment says just put the G, then 2 gaps, and then put the rest. A, G, A, and that lines up with G, T, T, A, G. Also a score of -7. You can see the score if you apply the penalties and reward parameters that you chose. Right? If we look at the first alignment, we would get a +1 for that G matching G. We would get a -1, a -1, a -1, a +1. We would get a -3 penalty for that gap, and we would get another -3 penalty for extending that gap. So if you add those up, it is -7. Same thing here, +1, -3, -3, -1, +1, -1, -1, -9, +2, -7. That's where this came from. So they listed out all the trajectories that wound up in the bottom right corner. I actually found a couple more. I don't know why they didn't put them in here, but That's the way it works. If you were, so this is DNA sequence. There's only 4 bases, relatively simple. When you do proteins, you have, let's say, 20 amino acids that make up the protein sequence. You can still do the same algorithm. You tell me what a match reward is, what a mismatch reward is, what gap penalties are, and we can throw this algorithm at it and come up with the alignment. A challenge with working with proteins, let me see if they talk about it in here. When you deal with proteins, it's more complicated because there are things that are known about, like certain amino acids are more or less likely to actually bind with each other. Certain amino acids are more or less likely to be physically proximal to each other, just based on their physical and chemical makeup. Like in this picture here, which is in the homework I mentioned that PAM30 penalty matrix. This is another thing like the PAM30. It's a PAM250. This is somebody else's choice of how to penalize or reward matches. And what this does is, for example, can't see my cursor. If you were to put an A with an R, a mismatch, according to this scoring scheme, you get a penalty of -2 if you look at the cell that corresponds to the first row, second column. If you were to put an A with an N, that's also a mismatch, but you don't actually get any penalty according to this scoring routine. And if you look through, there's some penalties that are really high. Can't see my cursor, but at W and D or C or E and G, there's high penalties, -7. And that's because those are, they are not compatible. Either they physically don't look like each other, the places where they would bind are, they don't match up, something like that. There's different likelihoods of 2 things coming together. There's also non-uniform match rewards. If you put this A with that A, you get a reward of 2, but that's not the same across the board. The very next one, if you put the R with the R, you actually get a reward of 6. All right. So you don't want to do that one by hand. It takes too long. Where did R go? Not writable.
Are we gonna do any examples of like creating a sequence, like your consensus mapping or anything like that? Overlaying a bunch of GBS data to figure out what the sequence of your is.
So I will show you with the muscle package that one of the things you can get out of that is a consensus sequence. So if you pass in 30 sequences, I don't know how it works with a huge library of sequences, but certainly for multiple sequences, you can align them and get out the consensus, the best guess of the whole thing. Do you have in mind like assembling an entire genome kind of thing, or?
Yeah, I was just wondering because we work in agriculture. A lot of our crops don't have reference genomes yet.
Mm-hmm.
So we're still working on it. And a lot of times when you have a population that you create, you have to create your own reference genome
Right.
for that population.
Right. I don't know if muscle is powerful enough, at least the bioconductor version of muscle is powerful enough to do like de novo assembly of an entire genome. I'd have to look into that. There might be another package that's more applicable. Or for something, so R is not going to be great at really big data sets, because what R does is load data into its memory so that it can quickly work and call things. So if you have an enormous data set full of lots and lots of reads, for example, it could get pretty slow in R. So that for really computationally intensive tasks like de novo assembly, might be ideal to use standalone software. Like, are you familiar with some standalone software, like for... Yeah. You lost the screen share? I had to do Task Manager to kill R. That might have done it. Okay. No problem. What's that? We will talk about false discovery rates. So this is what I was thinking might be better than trying to use R for such a thing. Something like Velvet, which is a standalone software package. These are optimized for this specific task of assembling a genome. The problem with them is that they're all their own thing. You know, it's not an R package, it's not SAS, it's some...
I'm not doing exactly this, but I was just wondering, sort of talking about Steve was saying, but so I have like 130,000 SNP markers, and I need to do a chip matrix of that in one of my programs. So that creates a matrix that takes like 8 terabytes of memory, of hard drive memory in R. So
You will not be able to do anything with an object of 8 terabytes, right?
So you have to, the only option in the package is to do GPU processing of a supercomputer, take it apart. So is there like anything out there where you can like kind of like send it somewhere else and repack other than doing GPU processing?
Okay, so question was, have a really large data set full of sequence data and I want to do a big alignment problem, basically. The data are too big to do in R because of memory issues, and then therefore is it possible to communicate through R with another software tool that could do the heavy lifting? Yes?
Yeah, like is there, I know you can do it,
Mm-hmm.
like certain, you can talk to certain software, so you make the package that way, but is there anything like built, is there any packages that are built to do that? Somebody's built to like handle that?
I don't know off the top of my head, but I can look. They're basically in R, it is pretty straightforward to communicate with other things. Most of my experience is with, you want to do a lot of calculations and it's going to take forever in R. So you start in R because it's easy to manipulate your data and everything, and then you dump it to C or C++, and you write your own C or C++ code. So then you get the benefit of the handiness of R, but the really computationally intensive stuff, which is like 20 times faster in C, you can do that, and then it just pulls it back in. The only, like, the mature mechanisms I know of for doing that kind of thing are specific to things like C and C++. So I'm not sure about if there was, like genomics workbench, CLC genomics workbench. I seriously doubt that there is a way to communicate with a proprietary piece of software like this, which costs lots of money, I think. But there might be for some of these other ones. So I'll have a look and see if I can find anything.
Yeah, I think the package I work with already sends things out in C++ and brings it back, but I have to make that huge relationship matrix, it just crashes. There's no way to do it.
So if I had a huge data set that I couldn't even read into R, I would look for ways to save that to a file, the data to a file, and if I wanted to use R, arrange for messages to be sent to maybe C or C++ that read in that data through those packages.
I can read the data and it's just making the relationship matrix like that, 1 for 1 to 1 for 1.
Mm-hmm.
So it's a huge matrix.
So maybe make that in a separate file. Use something, could be C++ for example, dump your data into C or C++. For reference, if you want to learn how to do that, let me show you. But dump it out there, dump the data, and then have C or C++ code that does the actual creating the enormous matrix and write that to a text file or a CSV file.
But it's so big, that's the problem. The memory size
Mm-hmm.
for the matrix is 8 terabytes.
Yeah.
Like that's not even processing, that's just hard memory.
Yeah.
Storage. So I guess you have to use the supercomputer or something that has that large hard drive.
Yeah, there's not, at some point there's not going to be, you're going to have to do parallel computing or pay big bucks for, professional software that knows how to do parallel computing itself. So, yes.
What about this GPU interfaces for R? If you can communicate with GPUs to R?
Yeah, you can.
Yes. So there is functionality in R to do parallel processing and send things out to multiple cores and things like that. As far as parallel processing goes, I think it's relatively easy, but that's as far as parallel processing goes, which means it can be complicated. It's not easy to do that. Yeah.
You can set things up to do them, which is NVIDIA's GPU processing, when you have to learn how to write CUDA.
You know, sequence big data, you can also have cluster account. Like they were like, they have like a 9 cloud systems.
Yeah.
Cluster. They work on that, basically we work on that because we also get sequences with the really big and
Yeah, but I don't really need to sequence it. Like I have reference genome, I was just asking that because we're talking about sequencing. My problem is that I have to make this matrix that is just so big that you can't do it. It would crash any computer if it wasn't one of its computers. It would never work.
The other thing you might consider, so still talking about enormous data sets, can't do calculations in R because it crashes because of memory and stuff like that. Another thing you could try is to break the problem up into smaller pieces. So instead of a 8 terabyte matrix, let's make 10 smaller ones that together fit the whole.
GPU processing is the whole purpose of core processing.
Yeah, but you could do that pretty easily just on your own without involving core processing. You could just like run the first one, to create text file 1, run the second one. To me, it would be a question of how much time do I have to invest to learn how to use this GPU stuff versus maybe I spend an afternoon and I just work up a hack on my own and just do it piece by piece. I mean, if you're going to be doing this all the time, it's probably worth it to figure out how to use some of these tools. This is what I was going to show you and then we'll quit. This is back at cran.r. Just Google R cran or R. And under manuals, there's several manuals. The first one is basic R stuff. There's one for how to import and export data. And then there's one for writing extensions. And in here is documentation on how to dump stuff to C, C++, Fortran. So I'll let you look at it. It's not that hard. It takes doing it a few times. So you can look through this if you want to. Basically, you call a function called .c++ or .c, and you pass in your arguments in a carefully, they have to be prepared in a particular way. They all have to be numeric or integer or character, I think. But it's not that hard. Okay, well, we are out of time. Hopefully now you can do this in your homework. The only other thing that we have not, I think, talked about that's relevant to your homework is putting a p-value on an alignment. So I think I asked you to assess the significance of an alignment. We'll talk about that next time, which is down below. This is all code that illustrates doing a pairwise alignment. And then a question is should I believe this alignment? Because these alignment algorithms are always going to give you the best alignment, even if the two things don't belong together at all. This is the best we can do, but that didn't say anything about whether it was like a believable alignment. That's a job possibly for statistics. We could ask something like, with these two sequences, you proposed this such and such alignment. How likely would it be to see, let's say, an alignment score of that, whatever you got, -7 or something, or even better, just by chance? If we had two sequences with this kind of composition, this length and that kind of composition of letters, if you were to just randomly shuffle or randomly create sequences like that and align them, how frequently would you get a score of -7 or even better, just by chance? And the proportion of times that happens, if you can simulate that, is a p-value. So if you do a pairwise alignment of these two sequences to each other, and you put a p-value on it, and you get a really small p-value, that's saying it would be very unlikely to see this strength of alignment just by chance. So then you could filter your aligned sequences, only take the ones that we're really confident in. So I'll show you how to do that next time. All right. Have a good weekend.